Okay, let's start. I'm trying. The recording went okay last time, I think, so we'll try it again. And it's already posted on in the Blackboard page under that section that says notes and videos. And then these notes there are also there, posted in PDF form. Is there anybody that was not here last time? Everyone here? Did y'all bring back your that little piece of graph paper that I gave y'all? Because we may get a chance to use that again today. Dom's looking sheepish here. All right. I think since I've got apparently some spare syllabi here, we can steal some from that. Okay. To use maybe if we're going to do that. Okay. So we've been. So what we're doing here, we've only been here one day, but what we're doing here at the start of the course is just kind of taking a quick tour of some of the different types of combinatorial type of problems that are part of this big subject of combinatorics, which, as I mentioned last time, is in just kind of a nutshell here is kind of the study of finite sets, right? And in particular, we're interested in determining the cardinality. That means counting the size of the finite sets, all right? And so a lot of the things that we're doing here in the class are going to be devoted to that sort of problem. But many times now, there are lots of variations on these combinatorial type problems. And so in many instances, we're not going to be just concerned with determining the cardinality of a finite set, but actually we'll just be concerned with is the finite set empty or not? Okay, so it doesn't have any elements in it, much less, can we count the number of elements? Are there any elements at all in the set that's being described? Okay, and then we'll see other sort of variations on once we've described some sort of a combinatorial setting, lots of other sorts of variations on the types of problems we may ask that are considered combinatorial type questions. But a lot of the times they revolve around determining the cardinality of a finite set. Okay. So last time we were talking about just a specific example of a combinatorial type situation, and that was tiling a chessboard. And chessboards really give us lots of good opportunities, or they're a really good setting for combinatorial type questions. So we're going to look at kind of variations on this problem of tiling a chessboard with, we talked about with dominoes last time, okay? And but today, also in the notes, we'll look at some other sorts of questions that we can pose that aren't tiling questions, but are based on chessboards, right? Okay, so they're in that particular setting, questions that we'll want to answer. All right, so I think last time we had sort of talked about or introduced there the basic question of building a perfect cover, right? Okay, of a chessboard with dominoes. So that was finding an arrangement of the dominoes on the chessboard, right? So it would cover all the squares of the chessboard. And then we were thinking of variations on that particular problem. Okay, and the first one that we were looking at, right, was the so-called problem of what happens when you prune the chessboard, and if it's possible to then build a perfect cover of that chessboard, right? So is it possible to tile the chessboard with dominoes? And this was this was the first example that we were looking at there. Okay, of course there's just a standard 8x8 chessboard, right? Okay, and in the original version of the problem, right, we weren't thinking about coloring the squares of the chessboard black and white like they would normally be, right, in a typical chessboard. But here I've introduced that coloring, right, so we have the alternating colors, black and white, for the squares of the chessboard. And that's not really pertinent to the question that I'm going to ask here, but it's useful in helping us understand the solution to the question. Okay, so the question is not going to be about black and white squares on the chessboard, but the fact that we've got the squares alternately colored black and white turns out to be helpful in finding the solution there to this question that I am going to pose, right? So here's what we're going to do now. We still want to tile the chessboard with dominoes, right? So remember, the dominoes cover 2 squares of the chessboard, and you can arrange them, right, in any way that you like, as long as they cover 2 squares of the chessboard, right? And so it's going to take a lot of dominoes here, right, to cover the chessboard. And there may be many different ways, right, of arranging those tiles on the chessboard, right? So arranging those dominoes on the chessboard. So that's kind of the basic finite set that we were considering, right? Is how many arrangements of those dominoes can we come up with to tile the chessboard. But now we're going to alter the chessboard in just a little way, right? I'm going to cut off diagonal squares out of the chessboard, okay? So I'm just thinking of this, right, virtually as cutting off this square, right, out of the chessboard in that top left-hand corner, and then also the bottom right-hand corner of the chessboard. Okay, so we're going to eliminate that from the chessboard, right? So we have to all do this kind of mentally, right, kind of virtually, because I don't have a physical chessboard here, and then, of course, I'm not going to saw off the corners of my chessboard, right? So so all of this we're doing just with models, right? Either on paper or like here, right, or mentally. Okay. But again, the same question there is I want to tile the chessboard, right? Okay. So again, I want to cover the chessboard with dominoes, all right? And so so this set here would be the set of possible tilings or perfect covers of this pruned or occluded chessboard. Okay. Now it's conceivable that we could have a tiling, right? Okay, because we do have the right number of squares, all right? So that basic condition is met, right? You're going to have each domino is going to cover 2 squares, right? Okay, so when you cover this chessboard with dominoes, that means you're going to be covering an even number of squares, right? Okay, 2 for each domino. And how many squares are we covering here? Well, in the original chessboard, there were 64 squares, right? Because this is an 8x8 array. This is an 8x8 grid, right? And 8 rows and 8 columns. But we take 2 off. So you have 64 minus 2, which is 62, which is still an even number, right? Okay, so it's at least conceivable that we could cover the chessboard, right? If I had only cut 1 square off, then immediately we could have said this set T is empty, right? It has no elements in it because we would have had an odd number of squares to cover, but you can't do that with dominoes covering 2 squares, right? Okay. So if I'd only cut off 1 square anywhere in the chessboard, if I had removed 1 square, then there's not going to be any perfect covers. Likewise, Shelby, if I had taken off 3 squares anywhere in the chessboard, right, okay, then that would have left me with 61 squares to cover, and there's no way to do that with without cutting a domino in 2, right, okay, which we're not allowing ourselves to do. So, all right, so, but we've got an even number here, so it's at least conceivable that this is it's at least conceivable that this is possible, all right, okay, but here's what we want to demonstrate to ourselves here. Actually, you cannot do it, all right? So this set is going to have cardinality 0, okay? So there is no way, even though there's 62 squares here to cover, right, okay, we're not going to be able to do this, all right? Okay, so why can we convince ourselves that, how can we convince ourselves that this is the case, right? Okay, and so that's what we're trying to convince ourselves, right, or prove to ourselves that the cardinality of this set is in fact 0, right? Okay, so when we try to count this set, it doesn't have anything in it at all to count. Okay. Now I claim the fact that we've got the squares colored, although that's not really pertinent to the tiling, right? Okay. It's helpful in the solution of the problem. Okay. So the fact that the squares are alternately colored black and white can help you discover why there's no tiling of this particular chessboard, all right? Okay, so I want you all to think about that together for a while, just for a few minutes here, and see if someone can come up with a convincing answer for me. Otherwise, we'll discuss it and see if as a class we can come up with a reason why that set of tiling is, in fact, empty, okay? It has cardinality 0, all right? You want me to show the picture again? All right, so the picture's really helpful. And again, you want to think about the fact that the squares are colored alternately black and white, okay? By the way, how many dominoes, if there is a tiling, how many dominoes would be in the tiling? 31, right, okay. So that's something that you know. If there is a tiling here, right, it's going to have 31 dominoes in it, right, okay? So use that fact as well, okay, to see if you can come. Now, you can discuss this with your friends, right? So you all need to talk about this, right, okay? And if someone has a solution immediately, then you can share it with around, right? Okay, that's fine. Otherwise, you know, 2 heads are better than 1, right? Okay, and actually, I think as the number of heads increases, the brain power also increases, okay? So I think that's a well-known, actually scientifically established fact. So so the more of you, I think, are talking about it there, the better it would be as well, okay? So see what you think there about that problem. Or maybe it's obvious. Maybe I'm just... maybe I'm insulting y'all's intelligence here. Y'all got yourselves convinced? Okay. Do you think if you give your explanation to the class, they'll be convinced? Well, in particular, will I be convinced as part of the class? Okay. All right. I'm a pretty tough audience, so all right. Okay. I'm a little bit dense, so I take a lot of explanation. Hi, Catherine. They're talking about this Prune chessboard problem. Okay, so all right, so it sounds like the noise was dying down a little bit there. So either you've given up or you've convinced yourself that this is the case. Does someone have a solution that they want to share with the class? So you have to come up. Okay. Yeah. All right.
Okay.
You can point.
All right. So kind of the way we're thinking about it is that with colorings and how they alternate,
Mm-hmm.
where each adjacent square is a different color.
Mm-hmm.
If you put a domino on a square and you like start one half is on like a black square, then the other half has to be over a white square, kind of direction.
Oh, that's right, right. So whenever you lay a domino down in your tiling right, it's going to cover one black square and one white square exactly right, okay?
Yes.
Because all black squares are adjacent to white squares and vice versa.
Yeah.
So there's no way to place a domino over two white squares or two black squares,
Yeah.
right, okay?
And since the way the squares are placed, there's no way for a domino to cover, two white squares or two black squares. So therefore, that kind of implies that there has to be the same amount of black squares as white squares. And since there's not, since we took away 2 of the white squares, there's 32 black squares and only 30 white squares. So since those aren't the same, there can't be a tiling.
Okay, I think you're right, but let's see if we can clear up some of the things that you said that were a little bit fuzzy there. All right, so let's think about this kind of backwards a little bit. Suppose that you're gonna say the same things. Suppose that you had a tiling, right? Okay, so suppose that there is one. Then it's going to consist of how many dominoes? We already discussed that, right?
Yeah, if you had one, there would be 31 dominoes.
31 dominoes, right. Okay, now you said each domino has to cover, though, what? One black square and one white square, right? So if you have a tiling, then how many black squares will you have covered with your dominoes?
If you have a tiling, you'll cover 32 black squares.
No. Yeah, with 31 dominoes, right, you would cover what? 31 black squares, right? Because each domino covers one black, right? And how many white squares would you cover? See what I'm saying? You must have 31 dominoes in your tiling, right? Yeah. So you would cover 31 black squares and 31 white squares, right? Because each domino covers both a black and a white, right? Okay, right. So you are covering 31 black squares and 31 white squares. But how many black squares do you have to cover? 32. How many white squares do you have to cover? 30, right? Okay, right, okay. So that's right. See that, right? So a tiling would cover 31 white and 31 black, but it must cover 32 black and 30 white, correct? So there's not one, right? Okay, that's what your conclusion would be. Okay, right. Is that what y'all came up with? Was that essentially the idea there? Okay, right. Okay, so you see how the black and white alternating colors there helps to solve the problem, although it's really not relevant to the tiling issue, right? By the way, that makes it kind of obvious, right, that if you take a prune chessboard and you want to have a perfect tiling of that, you must have in the prune chessboard, must have an equal number of black and white squares, right? Okay, so because that was the issue that caused us to not have a tiling of that prior chessboard, right? It had 32 black squares and 30 white squares left, right? That's not an equal number, right? So if you prune a chessboard and it still has a tiling, it must have the same number of black and white squares. So that's a necessary condition to get a tiling when you prune a chessboard. It's got to have the same number of black and white squares. But that is not sufficient. So you can prune a chessboard so that you have the same number of black and white squares, but you won't have a tiling. Here's an example that's from the book. Okay, so this is a little bit a shorter chessboard, though, a little bit smaller chessboard. This one's only, what is that, 5 by 5? Okay, so if you prune that a chessboard right, okay, you'll have an equal. So I'm going to take out these 3. You'll have an equal number of black and white squares, but you can't have a tiling there, right? Okay, because I'm sorry, it's 5 by 4. All right, that's important also. So if you cut off these squares from the chessboard, you will have an equal number of white and black squares, but you won't have a tiling. Why don't you have a tiling there? Yeah, you have one square isolated here by itself, right? So there's no way to cover that with a domino, right? Okay. So when you take a chessboard that does have a tiling, and this is a 4 by 5 chessboard, it will have a tiling, okay? But if you prune it in this way, even though you have an equal number of white and black squares, it won't have a tiling. Oh, by the way, why does the original chessboard have a perfect cover? Well, how can you cover the original one without cutting these off? What's an easy way? Just line them up, right? So you could cover these two, right? These two, and so forth, right? Okay. So the original chessboard does have a perfect cover, but I claim, well, we can see, right, that if we prune these 3 squares, right, not going to have a perfect cover, right? Even though you have an even number of white and black squares. All right. There's a note here that I wrote. So it says in chapter 9. Wow. Okay. So toward the end of the course here, we're going to learn. Let's see what conditions are necessary and sufficient for a prune chessboard to have a perfect cover. Okay, and that turns out to be actually a problem with important applications. All right. So that's why we're going to consider it again. In chapter 9. Okay, now I want us to back up a little bit here, though, and think about a couple of things a little bit more deeply that are sort of simple ideas, but I want to make sure that we understand them. Okay, we talk a lot about counting, right? A set. And as I mentioned, of course, you learn how to count in first grade, right? So this is a problem that you have solved very early in your mathematical education, right? How to count a finite set, okay? But as we discussed last time, right, our first grade methods for counting finite sets are not going to be so helpful to us in this class because the sets that we'll be working with are either extremely large sets, okay, and so they're hard to count like in the first grade manner, all right, or they're complicated in some sense, all right. The elements in the set have some sort of structure to them, and it's sort of difficult to understand kind of what the sets look like, actually, all right? And we're usually not going to be creating physical representations for these sets, so we cannot count them in the first grade fashion, all right? Now, okay, all right. So, but I want to step back there and just remind ourselves, okay, what we mean when we say counting in the first grade fashion, and what counting in the first grade fashion really is, all right? So I'm not saying you don't understand how to count, okay? You obviously do, right? You do it very well, all right? But I want to think about it a little bit deeply, a little bit abstractly here, so we understand exactly what we're doing when we're counting a set, all right? So I want you to put yourself back in to your first grade state of mind, okay? For some of you that may be easy, for some others may hard, right? Okay, but put yourself back into that first grade state of mind when you were first learning how to count, and what was the process that you went through to count a set, okay? All right, so I want a volunteer to demonstrate that process for the class, okay? So you know it very well, so you don't have to practice it because you practiced it millions of times. So I need someone to volunteer here for me and actually do some counting. And what we're going to count is the chairs in the classroom. Eduardo, you want to do that for us? Okay, all right. So step up here, all right, and I want you to count, but do it very slowly now, right? Okay, so we can actually observe what it is that you are doing, okay? So if I ask you to count the chairs in the classroom, I mean, what steps do you actually do?
I would start with the first one I see.
You start with the first one you see, and what do you do with the first one you see?
I say one.
You say one, right, okay? You say one, right? So when you say the first one you see, though, again, I want you to demonstrate for that class because you're looking at it, but you know, I want you to demonstrate for the class what is the first one you see, right? So how would you do that?
I'm assuming I'm going to go from right to left, I guess. Mm-hmm. The closest one to me, so I'd go one.
One. Oh, yeah, one, right. Okay, so but this gesture is really important. Right. Okay. Yeah. All right. So you're saying 1, right?
1.
Okay. Yeah.
I'm assigning.
So you're. That's right. So you're pointing that out, right? Okay, and saying, okay, that is desk number 1, right? And then keep going there.
1, 2, 3, 4, 5, 6, 7, 8, 9.
Yeah. Be very emphatic here.
Oh,
For me.
1, 2.
No. When I say emphatic, I mean really emphatic here, right?
Oh,
1.
like,
Yeah. Because I want the class to understand that you're doing this correctly, right? Okay.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, and 34.
Ah, perfect, right. Is that right? Did he do it right?
And
Do
then
you think that was
35 right
correct?
there. 35.
Well, no.
Oh.
I just want those,
You said
right?
chairs on
Okay, so all right, yeah, all right. So what Eduardo did there, of course, was he, and this is the way you count, right? I mean, this is typically exactly what you do, right? Okay, you will point out and say 1, right, and then 2, and then 3, and then 4, 5, right? Okay, and so on and so forth, right? So so what is it that you're doing there when you're going through that process? Okay, well, you're very clearly there, as Eduardo sort of hinted at, right? You're setting up a correspondence, right? Okay, you're setting up a one-to-one correspondence. Let me be careful about that, right? You're setting up a one-to-one correspondence between the chairs in the classroom and what set of numbers? Yeah, natural numbers, but what set of natural numbers? Starting where? At 1, right, okay, starting with the first one, and in this case, we went up to what? 34, right, okay, so we're creating a correspondence, a one-to-one correspondence, right, okay, between the chairs in the classroom, right, okay, and this set of integers from 1 to 34, okay? So whenever you're counting, that's exactly what you're doing, okay? You're creating a correspondence between a set of objects, right, and a set of integers, right, beginning at 1, going up to, well, whatever the cardinality of your set is, correct, okay? That is the process of counting. So it's creating a correspondence, right, between two sets, okay? The set that you're interested in counting, right, okay? And a set of natural numbers there beginning with 1, all right? So whenever we count, that's exactly what we're going to be doing, okay? We're going to be setting up this correspondence, right, between the set and this set of natural numbers. Now, in first grade fashion, of course, you do that by physically, right, sort of creating the correspondence, right, by saying this is 1, right, okay? So you sort of number things off, right, okay? So this desk corresponds to 1. This desk corresponds to 2, right? This desk corresponds to 3, and so on and so forth, okay? Since in this class, though, we won't be able to point at the objects explicitly, setting up this correspondence for us is going to be a little bit tougher, all right? But nevertheless, that's what we'll be doing in every case when we're counting set, all right? Let's add some formal terminology to that, okay? So here's a little description there, right, of first grade counting, okay? And what Eduardo did for us very nicely there was demonstrate this process, right, okay? The steps and actions he took, right, to count the chairs in the classroom, okay? All right, so now to associate just a little bit of mathematical terminology with this process, okay? Suppose you have a positive integer, so an integer bigger than 1, okay? Then if we take the set 1, 2, up to whatever that chosen positive integer is, okay, that set of positive integers, we're going to call that an integer segment, okay? So such a set 1, 2, 3, up to a given positive integer is called we're going to call that an integer segment, all right? A segment of the integers, okay? And we're going to denote that set by n with brackets around it, okay? So in this class, when I put an n with the square brackets around it, so this has to be a positive integer, okay? Well, a non-negative integer, actually, all right? This has to be a non-negative integer when I put the brackets around it. That means a set of integers, okay? Now, by definition, if I put the brackets around 0, which is not a positive integer, okay, right, okay? If I put brackets around 0, that's going to denote the empty set, okay? So by definition, this will be the empty set. But if for any other positive integer or non-negative integer other than 0, you can create the set in the fashion that I just indicated there. This quantity inside the brackets is going to be called the cardinality of the integer segment, all right? So the n is referred to as the cardinality of the integer segment. And whenever we count a set, right, that's not a set of positive integers, we just create a one-to-one correspondence between the given set and between that the integer integer segment. Okay, and the cardinality of that integer segment, we will call that also the cardinality of our given set. So, Eduardo, when you were counting the chairs, you set up a one-to-one correspondence between the chairs and what integer segment?
34.
34, right, okay. Right, okay. So you set up a correspondence between this integer segment and the chairs in the classroom. And you set up that correspondence, right, by just literally pointing out, right, and saying which chair corresponds to which integer. We may have forgotten now, by the way, which chair corresponded to which integer. Right, okay. So your correspondence there is not really foolproof in that sense, right, okay, because I probably can't reproduce it now. But nevertheless, that's what you did, right, okay. And so that's how we know the cardinality of the chairs in the classroom is 34, because, right, this integer segment for which we set up the one-to-one correspondence has cardinality 34, okay? Just that simple. Now, you can set up one-to-one correspondences with between sets which are not finite sets, okay? Right? You can create one-to-one correspondences between lots of different types of sets. If you set up a one-to-one correspondence between a set and the entire set of positive integers, okay, so that would be an infinitely large set, okay? So if you find a set, some set, and you create a correspondence between it has to be a one-to-one correspondence, so this is really important. If you set up a one-to-one correspondence between that, some given set, and the entire set of positive integers, okay, all right, then the given set that you started with is said to be a discrete set, okay, a discrete set. But if you set up a correspondence between your set and a integer segment, not the entire set of positive integers, but an integer segment, then your given set is said to be finite. So the set of chairs in this classroom is finite, right, Eduardo, because we set up a correspondence between that set and the integer segment 34, okay, all right. But if you set up a one-to-one correspondence between your set and all the positive integers, then your set is said to be, it's infinite, of course, but it's discrete, not finite, all right. Well, we're mostly going to be concerned, as we mentioned last time, right, with finite sets. All right, so do you understand better now what counting is? No, you probably understood it very well already, right? Okay, so you probably can't say you understand it better, okay? But you're getting ready to understand it better because, as I mentioned, right, as I keep stressing, these one-to-one correspondences are not always so easy to set up, okay, right? They're easy to set up, Eduardo, if you can physically create the one-to-one correspondence, right, okay, by pointing, right, okay? But if you cannot point to the objects and physically set up the one-to-one correspondence for whatever reason, then setting up the one-to-one correspondence not as easy, all right, okay? So that can be that's more challenging problem. That's the type problem, counting problem that we want to deal with in the class. Okay, now, also, we also want to think a little bit more deeply, okay, about another problem that's going to vex us here in the class. And that is, again, the objects that we're going to be counting, we cannot point to them, unfortunately, okay? So in some cases we can, but in most cases we will not be able to point to them like we counted the chairs in the classroom, all right? So we either have to manipulate them mentally, okay? Well, in most cases, we have to manipulate them mentally, all right? But it's not so easy to just always be, manipulating these sets in your mind, right? Sometimes you do have to be able to somehow express them on paper, okay, or in some form or another. We're just not so brilliant that we can just, completely rely on our brains, right, to work with these objects. So we just can't work with them virtually. So sometimes we need to somehow be able to write them down, okay? So we need to somehow be able to write, to represent or model the objects of a set that we cannot physically duplicate, okay? And that is going to turn out to be an important issue for us, all right, in the class, because that's often the key for counting the set, all right, is can we create some sort of model or representation for the set, even if we cannot physically construct the set, all right? Okay, so I want to practice that a little bit, okay? And the first problem is one that, especially if you play chess, you already may have a solution to this, okay? All right, so here's a chessboard, right? Okay, and we've been, of course, playing with chessboards here already in this first long example. Okay, and but we've been doing that by just really trying to diagram the chessboard, okay, on paper. So that is one model of the chessboard, right? Okay, just actually drawing the chessboard on paper. But that's kind of a clumsy model. It's just not easy to, or cumbersome model, right? Okay, so because chessboards have 64 squares in them. It's just not always easy to diagram chessboards. So we need some other mechanism for modeling or representing chessboards, all right? And so that's what I want you to think about now, okay, is how can you also model or represent the positions on a chessboard, okay, all 64 of them, okay? And if you can represent all 64 positions, then that's essentially a representation for the chessboard, okay? How can you do that without drawing the chessboard, without actually diagramming the chessboard, okay? So you see what I'm asking, Shelby? Is there some way to write down a representation for the positions on a chessboard, the squares on a chessboard, which essentially would be representing the chessboard, okay? If you could do all the positions, that would be the whole chessboard. Is there some way of doing that without actually, having to diagram the chessboard? Okay. All right. All right. Well, there's a. All right. So I'll let you think about that for a minute before you answer. But there are actually lots of methods for doing this because, of course, a lot of people play chess, right? Okay. So there are lots of different ways of modeling positions on a chessboard. But there are one way that's kind of standard. Okay. That's the most frequently mentioned way, okay? So if you play chess, you might be familiar with this, probably a lot more familiar than I am because I don't play chess, right? Okay, so, but if you don't play chess, that's fine. See if you can just devise something here, all right? And you can describe it to your friends, okay? All right, so let's take just a few minutes for doing that, okay? Because that's pretty easy to do, all right? You can use the magic Google machine, by the way, if you want to look this up on your smartphone. This is fine. It's going to tell you a lot of information about modeling chessboards, though. Okay, did y'all think of something? Anybody want to share their idea? Kaylee? A grid system? So, yeah, so there's definitely a grid there, right? Okay, so, but what, but...
So, like, vertically, it's A through H, I think, and then horizontally, it's 1 through 8, and then...
Oh, is it, so vertically, right? The columns are, you're going to label the columns? I think that's how it works, yeah, okay. So you're going to label, I mean, I think this is the standard system for doing this, right? So the columns you're going to label with letters, right, okay? But you could label them with numbers, I guess, right? So I guess this is A, B, C, D, E, F, G, H. Oh, yeah, okay, so you do your alphabet pretty good there, all right? And then what about for the rows here? Oh, with numbers? All right, so... And I think we usually number from bottom to top here, but I think this is in chess, but y'all correct me. It's usually numbered from, is it from the white to the black? Is that the way it goes? All right, so this will be the white side of the board, and this will be the black side. Okay, all right, so, all right. Right, and then any position you just represent as what? A pair, right? Okay, right? Which consists of, in this case, a letter and a number, right? Okay. Do the numbers go first or the letters go first? Oh, the letters go first? Oh, I was hoping it was the... But it really doesn't matter, correct? Okay, because you have you have different symbols for the rows and the columns, right? Okay, so because you have different symbols for the rows and the columns, it doesn't really matter, right? Which you write first, right? Okay, so this position we could write that as A1, but we could also write that as 1A, right? Because that gives you the same information, right? Okay, that's going to give you the same. That's going to give you the same position. These are called now. The columns here are called the files, right? And the rows in chess are called the ranks. All right. So you get the classic rank and file system, right? Okay. That's partially where that phrase comes from, right? Or that's a military phrase, right? Okay, but of course, chess is kind of a military game, right? So this is the rank and file system, right, for denoting positions on the chessboard. If you want, of course, you don't have to. You don't have to use letters, right? For the files, right? You can use numbers as well, okay? But then you're going to have to be careful about order, right? Okay, so if you use numbers there for the files, right, then then obviously, right, this position, right, okay, and this position would not be the same, correct? Okay, so the order of the numbers, right, would also give you information. Oh, neat. Okay, so let's think about with the numbers here. All right, since this is a math class, right? Okay, so if we use the numbers here to represent the columns. So if we've numbered the columns 1 to 8, right, and also numbered the rows there from 1 to 8, then what are these things called that we're using to represent the positions of the chessboard? Yeah, these are called ordered pairs, right? Okay. So here we could use a set of ordered pairs, right, to represent all the entire chessboard. So we can model the chessboard as a set of ordered pairs. All right. That's what I'm getting at. Okay, is some way of writing down the chessboard without actually having to or to talk about the chessboard, right, without having to actually diagram the entire chessboard. So we can think of the chessboard there as being this set of ordered pairs. And we can probably think of lots of other systems, right, for also for representing the chessboard, okay, or for modeling the chessboard. All right, so if we use the ordered pairs of numbers, then how would we model a tiling, a perfect cover? So what would a perfect cover look like? How would you model that set? Okay, so how can we write down a representation for a perfect cover or a tiling of the chessboard? Okay, you don't have to write down all the whole perfect tiling there, but what sort of things or what sort of items could you use, right? Objects could you use to represent tiling? What would a tiling look like? Okay, all right, so think about that for just a second and then describe that to me, okay? So if you had a perfect cover, what would that look like? So remember how many things have to go into a perfect cover? 32, right? Okay, because it consists of all those dominoes, right? So perfect covers are kind of complex things, right? Okay. Okay, does somebody can somebody describe for me there a method there for writing down a perfect cover? Catherine, can you? What now? A pair of a pair of pairs. Is that what you said? Oh, okay. So, all right. So, Catherine says in a tiling, right? Okay, you have all these dominoes, but each domino just really covers what? Two positions, right, on the chessboard, correct? Okay, so you can kind of represent a domino, right, as just a pair of positions on the chessboard, correct? Okay, so each domino is just a pair of those positions, but those pairs are what? Also pairs, correct? Okay, all right, so let's put a domino there, Catherine, and then let's write it down. So so there's our chessboard, right? Okay, so just put a domino somewhere. All right, so what now? 1, 1, and 1, 2. Okay, all right. So so she's going to put a domino. Is that right there? Right. Okay. So that would be over covering 1, 1, right? And then also covering 1, 2. But we have to make clear that this is an item, right? Okay. So we have to group those pairs together. All right. Now this is where sometimes things get a little bit tricky because we may want to group them together as an ordered pair, right? Okay. But when you group things as ordered pairs, order matters. So if I were to switch 1, 2, and 2, 1, I'm sorry, the 1, 2, and the 1, 1, right? Okay, that would really be a different, mathematically, that would be a different thing, okay? But in our board, is that really different? No, that would just be sort of maybe turning the domino over, or I don't know, okay, right, okay? That's still going to be the same domino, correct? Or the domino is still going to be located in the same position. So you really don't need order here, right, for these pairs. So if you want to group things together without order, that's called a what? A set, right, okay? So what we really have here is a two-element set, right, of ordered pairs, okay? That distinction now is going to turn out to be really important to us. So I know it seems kind of trivial, and sometimes it's not important, but sometimes it is, okay? So so let me picture this as a set, all right? Let's put another domino in there, Catherine. So where do you want to put your next one? What now? 3 up here? 3, 3, and what? Oh, so these two? Okay, all right. So I thought you were going to go right down the road there, but so 3, 3, and 3, 4. Whoops. Oh, no, that's right. Okay. So 3, 3, and 3, 4. I should change colors here, but all right. So now we've got a domino right there. Okay, right? But that's not a perfect cover, right? That's just 2 dominoes in the perfect cover. So we have to keep going here until we've gotten how many of these dominoes? What now? 32, right? Okay. So we have to keep adding here until we get 32 of these things, right? So you see a perfect cover is going to be let's see, it's a set of 32 sets of what? 2 ordered pairs, right? Okay, yeah, that's right. So it's a set of 32 sets of 2 ordered pairs, right? Okay. So see, it's got a structure to it, right? Okay. It's set a certain size of ordered pair. Of sets of ordered pairs, and the sets of ordered pairs have to have 2 things in them, right? And they each have to be ordered pairs. Just pretend here for me, Catherine. What's the last domino that you put into this, into your perfect cover? What now? 8? What'd you say? 8, 8. Am I doing this right? No, no. 8, 8, and 8, 7. This one up here? Oh, all right. So the top right-hand corner there. Okay. All right. So 8, 8, and 8, 7. Ah, there you go. All right. And we'll just imagine that all the others are in there beautifully right. Okay. So we have 32 of them. Now, if I gave you a set that matches these criterias, right, how would you check to see if it's a perfect cover? Because I can write down lots of sets of subsets of ordered pairs, right? Okay. What now?
Make sure none of the sets, like the sets are disjoint.
Oh, so you can't have identical sets here, right?
Correct.
Okay. Yeah. So you couldn't have identical sets here, because that would then we'd be stacking a domino on top of a domino, right? Okay. So we won't have that. What else?
You also have to confirm that each pair, like each set of ordered pairs is like a valid domino.
That's right. So you would have to make sure, right, that all of your chessboard, right, okay, all of the ordered pairs in your chessboard, correct, are somewhere here, right, okay, in this big set of order, in all these sets of ordered pairs, right, okay. So you have to make sure that every ordered pair in your chessboard is there. That's not just that, though, okay. What else would you have to check?
So you'd have to have a rule stating like how odd numbers, well, I mean, in that one, odd numbers are black squares and even numbers are white squares, but you'd have to have a rule that if you have one ordered pair, well, in the ordered pair, it has to be like one number and then the same number, or if that's an even, then that has to be an odd. If that's an odd, that has to be an even.
So in other words, is that what you were going to say?
I was going to say you have to make sure that your two parts are adjacent to each other.
That's right, yeah. So, yeah, that's what you were saying, Kaylee. You have to make sure that your pair here, right, your two-element subset is really a domino, right, okay, right? So you got to make sure that it really is a domino, right, okay, which means that these ordered pairs have to be adjacent, right? So what's going to make them adjacent?
If they're either the same number or
Yeah, what is it? Is it that these coordinates have to be the same, and these are different by what? 1, or these coordinates are the same, right? And these are different by what? 1, right, okay? So you would have to go through all 32 of these, right, and make sure that they're actually, in fact, dominoes, right? Okay, yeah.
Do you not have to, like, denote that a domino is a part of the set, or is that just extraneous information?
That a domino is a part of the set?
Yeah, like you have a certain number of dominoes to cover.
Yeah, we'd have to have 32 of these, right? But that would happen if, I think, if his condition is met, which is all of the ordered pairs in the chessboard are in one of the two-element subsets. Okay, right? Okay. So just because you have this this big 32 two-element subsets, right, doesn't mean that it's going to be a perfect cover, correct? Okay. However, so here's a question we want to take up, right? Is we talked about how many perfect covers there really are, right? Okay, of the chessboard. It turned out to be some huge number, right? Okay, wasn't it 12 million and something? Yeah, almost 13 million, right? Okay. So that's a difficult number to count. So that wasn't really discovered until, I think, the early 1960s. All right, so that's a hard number to count. But I think we will be able to count how many sets like this that there are. Okay, so that would be sets of 32 two-element subsets of ordered pairs. Okay, now a bunch of those will not be perfect covers, however. Okay, a bunch of those won't meet these conditions. But I think that set will be able to figure out how to count that set. Okay, that will also be a finite number, and so then we will have demonstrated that, oh, the set of perfect covers is finite, right? Because the set of all of these 32 two-element sets of ordered pairs is a finite set. Okay, so we'll revisit that a little bit later here, pretty soon actually. All right. Oh, y'all did that excellently. So y'all very smart. So now I'm expecting great things. Okay, that makes me think about the homework now. Okay, so we've got a week. We got a day off on Monday. Okay, so I think then. So for next Wednesday, then we should maybe think about having the homework due. So maybe let's talk about the homework on Wednesday of next week then and see where we are. Okay, on that. There are a couple of problems on the homework now that. I want to point out they're not in the textbook. So what did I do with the homework? They're not in the textbook. So they're problems that I'm just giving you here. And I just want to make sure we understand them. Let me show them on .cam here. All right, so first you have some problems from the textbook, okay? All right, so those are in the textbook. Now, in general, when you're working on the homework, I know you're going to be able to find the solution set, the solution manual for this book online, okay? Got to be. Because this is a famous book, all right? So I know you're going to be able to find that somewhere. Oh, it is? The solutions?
I don't know about the solutions, but the textbook is on, and the solutions in the textbook should be.
Yeah, the solutions are not in the textbook, I don't think. But well, I haven't looked actually, but I don't think they're there. But but I'm sure you can find them, okay? Because this book is no, I don't see any solutions here.
Usually, if you Google it,
Oh no, there are hints. Yeah, there are some hints, okay, but they're not really answers. All right, but yeah. Oh, that all you have to do is just Google.
Google it. A lot of times, people have just Yahoo answers. Sure, it's not always correct, but just double check.
Okay, all right, yeah, well, all right, so, what I want you to do is, of course, try to avoid those, right, as much as possible, right? The point of the homework is not the score that you get on the homework, it's the practice that you're going to get, right? So we're going to talk about the homework problems, right? You're free to talk with your friends about the homework problems, free to come to ask me in my office about the homework problems. So for your own benefit, don't just look at the answer somewhere, okay? Now this one, well, you may find this one online also, all right? So this is not a textbook question though, okay? But it relates to what we just did. So suppose you have a six-sided die, that's a single dice, right, okay? So just a standard dice, right? So of course, the faces are numbered, with the little dots, 1 to 6, correct, okay? But what we're going to do now is paint that die, okay? And we're going to paint the faces of the die either red or blue. These are going to be UHD die. So we're going to paint them either red or blue, okay? And, all right, so you've got the die is, every face is painted either red or blue, but it can be a combination, right? It's not that the whole die is red or the whole die is blue, right? Okay, so some faces can be blue or some faces can be red, right? And then, of course, you've got the dots on the faces as well, right? So I want you to see if you can write down a model, right, for a model, right, on paper, since, we're not actually going to paint the die, right, okay, for the different painting schemes, okay? Right, so see if you can write down a model for the different painting schemes. And then once you've got the model, see if you can then figure out what the cardinality of P is, that set of all possible ways to paint the die. Once you see the model, Eduardo, then you can kind of use your first grade counting skills, right? If it comes to that, because you can just, once you've got the model written down, you can just sort of say, oh, 1, 2, 3, you can sort of just number off, you see, okay, if you've got the model in front of you, right, okay? Now, but you may be clever and be able to figure out what the cardinality is going to be without actually having to count them all off, but it really helps to have them, to sort of visualize them in some way, right, okay? That's what writing the model down is, okay? Y'all were so good at the chessboard and the perfect covers, you won't have any problems with this, okay? Because our models often consist of sets and ordered pairs, right? Those sorts of things we use frequently to build models, right? Someone have a question? Y'all look kind of quizzical there.
Is 3B and 3C the same thing? I mean, a die is...
No, okay. 3C is, yeah, what is the difference there? So this is a die, but a die is a cube, but a die is a particular type of cube. Because what's special about a die? A six-sided die. There are other types of die, by the way, but a six-sided one, what's special about it? They're numbered, right, okay? They've got the dots on them. So if you just have a six-sided cube, you don't have dots. So that means that all of the faces kind of look the same, right? Okay, right? They all look the same to you, right? Okay, because they're not numbered. So, if you turn the cube, you really can't tell what face you're looking at, you see, okay? Right. That's right. So something has changed here, right? Okay. So suppose you have a cube, and again, you're going to paint, all right, the faces of the cube. But now we're going to paint one side black. So one side is going to be painted black, and then the other 5 will be painted either red or blue, any combination of red or blue, okay? I want you to see now if you can enumerate the different painting schemes in this case, all right? Enumerate the different painting schemes. So what's the difference here? Kaylee, why is the...
Well, for the die, I guess it's already, it'll be easy to assign colors because you already have the sides labeled.
Right, that's right. Mm-hmm. Yeah, but in the C version, if you see, so you paint the die, and if you turn the die... right, okay, you really, that makes really no difference, you see, okay. So the orientation of the die is...
The orientation of the die matters, the orientation of the cube does not.
Yeah, that's right. Orientation of the die matters because the faces are numbered, but in the cube, all the faces are the same. So 2 painting schemes that would be different in the die will be the same in the cube, okay. Right, all right, because rotating the cube is irrelevant, okay? Except remember, one side is black, so that's important. Yep. All right, one side is going to be black. Okay, all right. So think about that one. Now here's another problem. All right, all right. So we're going to build this exotic house. All right, this very modernistic house. All right, so it's got an inner courtyard here. So this is an inner courtyard, and then it's got 5 rooms, and then, of course, this is the outside of the house, right? Okay, so the inner courtyard, and then the 5 rooms. Did I count those right? Yeah, and they're connected in different ways by doorways, all right? Okay, as shown in the diagram. So that's a doorway, all right? Okay, now here's the set that we're interested in. What we want to do is tour the house, all right? So think of ourselves as a real estate agent trying to show this house to a buyer, and so we want to tour the house and go through every single doorway one time, okay? One time only, all right? And visit every room of the house, right? Go through every doorway one time, and of course, we don't want to get stuck in the house, so we want to start on the outside and end up on the outside, right? Okay? That is the issue, okay? So our T is going to be the set of all of those possible ways of touring the house, okay? But you have to go through each doorway only once, Start on the outside and end up on the outside, okay? All right. Now I want you to see if you can enumerate T, okay, for me. And and then we're going to change the problem slightly. Suppose that... we add one extra door. So it says add an extra door connecting room, maybe we're taking it away. The door connecting room 5 to the inside is moved to the outside. Oh, I see. So we're going to switch this door from here to here. Does that make any difference to T? All right, the set of possible tours. So if I move this door from here to here, okay, how does that change that set T? All right, so I want you to think about that, okay? So these are problems just for you to play with, right? Okay, so you may have to be using your pencil here a lot, okay, to think about this this problem. Okay. All right. This problem is due to Leonard Euler, the mathematician Leonard Euler, who worked in the 1700s. And we have another. Euler is instrumental in the beginning of combinatorics. And so we're going to see another Euler problem here shortly. Let me describe two other chessboard type problems, though, for you before we leave the chessboard behind. Okay. So as I mentioned, chessboard's a great problem for a great setting for combinatorial problems, but the whole problem is not the whole class not about chessboard. All right. Okay. So a traversal of a chessboard, all right, is if you start at the top row and move through squares of the chessboard to the bottom row, but you don't go up. Okay, so you can go left and right and down, but you cannot go backwards. You cannot go up. All right, that's called the traverse. That's called the top to bottom traversal of the chessboard. Okay, so you have to assume that the chessboard has an orientation, right? There's a top and there's a bottom, like we see here. Okay. All right. So here's an example of a top to bottom traversal, right? Okay. So we go through these squares. Now we can go to the left or right as much as we like. Okay. But we cannot go back up once we've started in a traversal. All right. So here we just go there, then we move over, then we go down some, then move over, then down a little bit. Now we can go back to the left, right? Okay. But you cannot go up. All right. And then we just come down. Okay. So there's one example of a top to bottom traversal. Now you can also build a left to right traversal. Kind of the same idea here, right? You start on the left column, and you're going to move to the right column, and you can go up and down as much as you like, but you cannot go back to the left once you start, right? Okay. So in a left to right traversal, starting where you want on the left, right? Okay, but you move to the right, and then you can go up, right, and you can go down as much as you like, but you always have to keep moving to the right. Okay, you cannot go back to the left. Okay, so a path like that is called a left to right traversal. Now, if you combine a top to bottom with a left to right traversal, you get a complete traversal, what's called the complete traversal of the chessboard. So a complete traversal is both top to bottom and left to right. So Shelby, if we have a complete traversal, where do we have to start? Yeah, that's right. Okay, you have to start in the top left, and you have to end up where? In the bottom right. Okay, you have to end up in the bottom right. Okay, and you cannot go
Back left or back up.
or up, right? Okay, so you're always forced to go down and to the right. Okay, so every move would have to be down or to the right. Okay, no up or left moves in a complete traversal. Let me see if did I draw an example here of a complete traversal? No, I didn't. Okay, but you can imagine there. All right, what a complete traversal looks like. So you have to start. This is not a complete traversal, right? Because it doesn't begin at the top left hand or end up here. Now, in many, as we've already seen, right, in some of the examples that we've looked at so far, it's not so hard in this case to convince yourself that the set of all complete traversals is non-empty, because you can write down lots of complete traversals easily, right? Okay, all you have to do is start in the the top left-hand square, right, and then just put yourself in the bottom right-hand square, right? Okay, just not moving to the left or up, right? So it's easy to draw a complete traversal of the chessboard. So it's non-trivial to see that, this is a non-empty set, right? The set of all complete traversals. So here's one where we really do want to try to determine what is the cardinality of that set, okay? So that's a problem that we're going to not take up immediately, okay, because this is a big number, all right? but there's a problem that we're going to eventually consider. Okay, how many complete traversals are there of a chessboard? All right. Okay, we're going to learn techniques for counting that. Now, another fun idea here you can define for chessboards is what's called a tour. Okay, so with a tour, you're going to visit every square of the chessboard. Okay, you're going to visit every square of the chessboard. So that's a path that covers every square of the chessboard. Right? So a traversal is not a tour of the chessboard, okay, right? Because in a traversal, you don't visit every square of the chessboard. But in a tour, we're going to visit every square of the chessboard. So some path that visits every square of the chessboard, that is a tour. So what's a simple example of a tour? Yeah, just snake your way down, right? Okay, so you can go start here, right, go across the top, then across, right, so on and so forth, correct, right? So that would be an example of a simple example of a tour of a chessboard. But of course, you can think of lots of different ways of visiting every square on that chessboard. Okay, so again, that's kind of determining that the set of tours is non-empty there is that's easy. Okay. So maybe the more interesting problem is counting how many tours there are, so determining the whole cardinality of that set, or putting some additional restrictions on your tour, okay? That may make the problem more interesting. That's what we're going to do here, all right? So here's the restriction that I'm going to give you, okay? Suppose we want the tour to begin in the top left-hand corner. The tour is going to begin in the top left-hand corner and is going to end in the bottom right-hand corner. All right? So we want a tour that begins in the top left and ends in the bottom right. Oh, by the way, you can't visit a square twice, okay? So you can't retrace your steps in a tour, right? Okay? So we want it to top left to the bottom right, okay? So let's consider just tours like that, okay? Here's what I want to know. What can we say about this set, the cardinality of this set? Okay, so tour that begins in the top left and ends up in the bottom right. Okay, yeah, oops, we're out of time. I'm sorry, so let's stop. Ooh, y'all should have stopped me sooner. What, Kaylee, do you have a question there?